Okay, so today I will go through this proof of Cauchy theorem, but is it on? Okay. Yeah, so I'll go through the proof of Cauchy theorem, which was basically the statement that that if I have there is some region, let's say there is I should first define something else. There is a notion of so suppose I have a region here, some region. There's a notion of simply connected or not simply connected, or not simply, the opposite of course, not simply connected region. What it means is that if I take 2 points here and start considering all possible curves, which contours which go from one point to another point, then you can continuously deform this contour to other contour. Okay. I mean, an example of in that case you say the space is simply, that region is simply connected. Okay. However, I mean to give an example of a situation where it is not simply connected, suppose there is a hole in this region. I mean this is not part of the region. Okay. In this case, obviously this contour I cannot deform to that contour, because in order to do that I have to pass through the hole, but that hole is not in the region, right? So that would be an example of not simply connected. So the Cauchy theorem is for simply connected region. Okay. So Cauchy theorem is for simply connected region. Okay. So what we are saying is that suppose there is a function, analytic function f of z, which is analytic in a simply connected region. Okay. So fz is analytic in, say, simply connected region. Let me just call it R, in R. So this is some region. Let's say this region R, some big region here, where it is simply connected, and we assume that there is a function f of z which is analytic here. Okay. In that case, what the theorem says is that if you take any contour, so take any contour, any closed contour, say C, which is entirely contained in R. So just as an example, I mean, just choose some. So this is my region where it's simply connected, and I just choose some contour, closed contour C. Okay. Then the claim that the theorem says is that the integral of f of z dz evaluated on that closed contour is 0. This is the basic theorem. Now the proof of the theorem, which is given in the book, is I think quite complicated. I will not follow that route. I will try first to prove a theorem called Stokes Theorem, which is in any way good for you to know. I think some of you already know about Stokes Theorem, but I will repeat it again, because Stokes Theorem has a validity much more than, I mean, it is not just for the plane. Stokes Theorem is valid for any n-dimensional space. Okay. So I mean, it has a lot of application. So I will first prove the Stokes Theorem, and then the Cauchy Theorem becomes almost immediate. Okay. But as I said, Stokes Theorem can be applied to arbitrary dimensions. So it's very useful for physics. So what is Stokes Theorem? So okay, so I'll start from Stokes Theorem. And again, I'll prove the Stokes Theorem in 2 dimension, and then I will just mention that this can be generalized to arbitrary dimensions. So the Stokes Theorem is the following. So suppose I consider, so I take again a simply connected region. Okay. And I consider, and let me first do a kind of a rectangular contour. This is a closed contour. It's rectangular. So imagine this is my x-axis, and that's y-axis, and this point is say x1, this point is x2, this point is y1, and that point is y2. Then I consider a contour which is like this. Okay. So I am going to integrate something, and I will define to you what I am going to integrate. So now consider a vector field. Consider a vector field. So there will be two components, because it's 2 dimension. A vector will have 2 components, right? So let me call it v1 and v2. Each of them is a function of x and y. Okay. This is the. I mean, there's usually people. Maybe I should write. Yeah. Actually, let me put here vx, the x component and y component. One way to think about this is that you define a vector field v as the following thing: vx dx plus vy dy. Okay. So this is just a definition. I just called this. I mean, I don't want to talk about that, but this is what is called a one form. Okay, because it has one differential. Each term has one differential. Okay, this is called one form, but I don't want to do that, because that will take me to something called differential geometry. So I will not discuss that. But for the present purpose, I just defined this v, which is simply vx dx vy dy. Okay. By the way, this notation is also very clearly explains how the vx and vy will transform if you change the coordinates x and y. Okay. So I mean, in a different coordinate system, suppose I change the coordinate x y to x prime y prime. Okay, which themselves are functions of x prime y prime are functions of x and y, and vice versa, x y are functions of x prime y prime in some region. Then I mean, this in the new coordinate system, again it will be some vx prime dx prime plus vy prime dy prime. Okay, and then you can immediately work out what is the relation between this vx prime vy prime to vx and vy by just the usual change of variables, because dx prime I can always write as dx prime divided by, I mean, partial derivative with respect to x dx plus dx prime dy dy, right? Because after all, x prime and y prime are functions of x and y, so I can express a differential with respect to x prime in this way. And similarly, dy prime we again express in the same way, dy prime dx plus d y prime dy. Substitute that here, okay, and then look at the terms which come with the dx, right? So what it will be? So I can put them together. Dx comes with vx prime dx prime by dx plus the term which comes from here, right? So which is vy prime dy prime dy, right? Plus similarly dy, you put together vx prime dx prime by dy plus vy prime dy prime by dy. Okay. So then what it is? So what we are saying is that now compare the two expressions. Then you see vx is that, and vy is that. So this is the way the vx vy are related to vx prime vy prime. Okay. So this is a convenient notation, because this notation immediately, this way of writing it immediately tells you how this v transforms. Okay. Actually, this transformation is a covariant transformation. This is the way a covariant vector transforms. So this is a covariant vector. For the contravariant vector, I mean, I think somebody asked about the covariant and contravariant. I think there was some discussion about it, right? So this is the way the covariant vector transforms. This transformation law is of the covariant vector. On the other hand, suppose you want to write down a contravariant vector, let's say W, which is a contravariant vector. Okay. This you write as Wx d by dx plus Wy d by dy. You define this vector. Okay. And then if you go to another coordinate system, this will be some Wx prime d by dx prime plus Wy prime d by dy prime, and then once again you can change the variable. I mean, write d by dx prime by using the usual chain rule of differentiation, and again compare. So that will give you a relation between Wx Wy to Wx prime Wy prime, right? And that relation is the one which is satisfied by the contravariant vector. Okay. So, this is the difference between covariant and contravariant. Covariant is a differential, okay. Contravariant is a different, I mean, is a derivative vector field, is a directional derivative. You see, what is the meaning of that, this object? This is saying that this gives you a direction in which you are taking the derivative, okay. So, it is a directional derivative, whereas this is some differential, okay. In classical mechanics, so this one is like the velocity and that is like momentum, okay. These are examples of contravariant and covariant vector fields. But okay, this was just so okay, going back here, there's V, and what I want to do is I want to integrate V over this contour C. Okay, it's a closed contour. Sometimes we indicate something like this to indicate that it's a closed contour, right? So just by looking at the symbol, you understand it's a closed contour. But sometimes I may not write it. But okay. All right. So let's evaluate this on this. So what will it be? It has 4 segments, right? So let's call it the first segment, second segment, third segment, and the fourth segment. Right? There are 4 straight lines which. So this total integral will be integral over the first segment plus the second segment plus the third plus fourth. So let's compute the first segment. So in the first segment, this you see this starts from x1 y1 and goes up to x2 y1, right? So y1 is fixed, y is fixed in this curve on this line. So the integral is really from x1 up to x2, where y is fixed to be equal to y1, right? And we are integrating this object, but notice that along this path, along this first segment, dy is 0. There is no, y doesn't change. So only the first term contributes. So you get here, so just Vx dx. Vx of course is a function of, each of these is a function of x and y, right? So what it will be x, but y is fixed to be y1, right? So it is y1, okay. And then you have dx, that's the first segment, plus similarly you write down the second segment. In the second segment you have y1 up to y2, okay. And then you have, that is this time x is equal to x2. So only the second term contributes because dx is 0. So you get here vy x2 y dy, okay, and then plus the third segment. In the third segment it is again this time y remains fixed, so only the first one contributes. So you get here Vx, and the value of y is now y2 dx, and this is going from x2 to x1, right? But x2 to x1 I can write it as x1 to x2 with a minus sign. So this is the same as minus x1 up to x2. And finally the last segment, which is the fourth segment. This time the x remains fixed, so only this contributes here. So vy vy, and value of x is x1, and then y dy, and this time is going from y2 to y1, which is the same as minus y1 to y2. So this becomes minus y1 up to y2. So this is the integral, okay. But now let's consider another integral, and I will show that integral is going to give the same result. So okay, so I now do another integral. So given this vector Vx Vy, I can define a curl. You know the curl, you know what is a curl. So define this quantity dx Vy minus dy Vx. This is what is called the curl. Huh? This is usually denoted as like that. Okay. So anyway, let's even without this notation, just consider this quantity, okay, and integrate this quantity. This is a true form, as you can see. There is a, I mean, if you write it, if you remember we wrote it as Vx dx plus Vy dy, and what this is you can write it in the following way: dx Vy minus dy Vx dx dy. Okay, this is a in fact in the usually the notation is this. This whole thing is denoted by dv in the, again in differential geometry, but this is not important for the time being. Just consider this and integrate. This is a two-dimensional integral dx dy, but inside this region which this contour is encircling. Okay, inside this let's call this region as R. So R is the region which is encircled by this contour. Okay, so I'm going to integrate over R. Let's integrate this quantity, and what we'll show is that this is equal to that. So this is in fact this will be the Stokes theorem. Okay, so let's do that. So we have two terms. Let's do one by one. So this is now a total derivative in x, right? So therefore, the first integral is simply you can integrate the x part for the first term. You can integrate the x, right? So this is a total derivative. So it's going to just give you the endpoints of the x, right? It will be simply v evaluated at vy evaluated at x2 y minus vy evaluated at x1 y, and then I have to integrate still dy still I have to integrate, right? Because I only integrate the x first. I use the fact that it's a total derivative in x, so I could integrate easily, right? So this whole thing, and then I have to integrate the y, which is going from y1 up to y2. That's the first term, right? Now the second term, there's a minus here. Now there's a total derivative in y, so I can trivially integrate the y first, and I will get the two endpoints. So that will give me, but dx is still left over, so I leave dx as it is, and then here vx evaluated at x comma y2 minus vx at x y1. These are the two endpoints in the y direction, right? Okay, and this x integration is of course from x1 up to x2. This is the result of that integral, right? So of course in doing so I'm assuming that these partial derivatives are all well defined inside this region. Otherwise you cannot do that. I mean if these are not well defined, then there is no, you cannot even define this quantity to begin with. So I'm assuming that this is all defined here inside. The partial derivatives exist inside, and that it's integrable, etc. Okay. Now I compare the two expressions. You see exactly the same. So let's see the vy. This term is that, right? This is the same as the second term here. Okay. This one is the same as the fourth term with a minus sign. Notice also the minus sign. And here this is the same as the third term, that's including that minus sign, right? And that one is the same as what is it, the first term, right? Including the sign, because there's two minuses, so it makes it plus. So that's the first term. So that's the basic statement, that this integral is the same as integral of v over the contour. And this, what is this contour? Contour is the boundary of this region, right? This region is R, and this contour is the boundary of the region. Sometimes one writes a contour which is a boundary of a region as dr. I mean this notation. This notation is meant to just say that this contour is the boundary of the region R. Okay, this is a notation, just a what do you call it, shorthand notation. Instead of saying boundary of the region, this is a shorthand notation. Okay. So this is this is basically the Stokes theorem. Okay, I have proven this only for the rectangular shape, because rectangular shape is easy to prove like that. But you see, you can extend it to any shape. I mean, just imagine any shape. Suppose I have whatever, some shape like that, the contour. Suppose this is my contour. You can always subdivide this contour, I mean this region, into little rectangles, no? Even in the boundary, you see, okay, this doesn't, you can make a smaller rectangle, and so on, right? Now, you start doing the integral. So I have all these rectangles here. You start doing the integral for each rectangle, okay? But what is going to happen? So there is a contour integral like that for this. Maybe I should make it slightly bigger so that you see it, otherwise it's more difficult to see. So imagine I have one rectangle like that, another rectangle like that, another rectangle like that. They don't have to be of the same size, doesn't matter. Another rectangle like that, and so on. So now similarly another rectangle like this. Now consider the integral integral inside this rectangle of this quantity, okay, then that is, by this theorem, is already saying that that's the same as the contour integral around here, right? Now consider this rectangle. Well, again, integrating over that is the same as the contour integral this way. Okay. Now look at this common thing between these two rectangles. There is this boundary which is common. So from this point of view, there is an integral along this direction. From this thing, there is an integral around that direction. So they cancel, right? So this way, you see all the interior, all the curves which are inside, all the boundaries which are in the interior, they are cancelled. For example, this will cancel when you integrate over this part. There will be Stokes theorem will tell you that this result is the same as that. So this again will cancel. So they will all cancel, and finally what will be left over is just the outer boundary. I mean, you may say that, okay, what about this curved thing? Well, you can make smaller and smaller rectangles, you know, very, very as small as you wish. So the error will be, you can make the error as small as you want. You know, for any epsilon, you can choose tiny square rectangles so that the error is less than epsilon. Error between the statement that the integral over this curve is the same as, the integral over this region or this quantity is the same as the integral over this curve, the full curve. That you can prove by this, by just drawing the rectangles. In fact, in the theorem, which is in the way it is proven in the book, they spend a lot of time in showing to you that you can indeed do this thing. This way you can approximate the curve as a curve by just kind of rectangles or squares. In fact, they do it squares. But, you know, so that you can do. But I think intuitively it's clear. You can, you know, because the size of the square you can make as small as you wish. Okay. This theorem, although I have proven it for 2 dimension, you can extend it to any dimension, right? Okay. But before that, let's see, is there any question here before I erase this blackboard? Yeah. Which one? Sorry, this one? This no, sorry, yeah, this is x. Okay. X. Yeah. It's a curl. Yeah. Okay. More generally, you can define actually in any dimension. Suppose I have some let's say a covariant tensor. Okay, I mean this is a covariant vector, but if you start putting more and more indices, you can get covariant tensors. So let's consider this some nth rank totally antisymmetric tensor. Okay, and I'll write it like this: V, let's say I1, I2 up to In. This is totally antisymmetric. In the, I mean, the space may be some space will of course has to be bigger than, greater than or equal to n dimensional. The way where you are considering this tensor, right? Because it's totally antisymmetric, so all of these indices have to be different from each other, right? So the dimension of the space in which this tensor is living has to be greater than or equal to n. So the dimension of the space is going to be greater than or equal to n. If it is n, then we know, we already have proven, remember in the first chapter, if it is equal to the n, then it is the same as, it's proportional to epsilon tensor, this Levi-Civita symbol. But in general, it could be, you know, higher than n. The dimension could be higher than n. Okay. Actually, I will take it to be greater than n plus 1, greater than or equal to n plus 1. The reason I will just do this. So this I can write again in the same way, xi1 dxi2 dxin. If you multiply that, yeah, you see these are all totally antisymmetric. So this, yeah, it's kind of, I don't know, it's not so important, but let me write it like this. I mean, so this is understood to be antisymmetric. in these differentials. This is called wedge. Wedge just means that they are totally antisymmetrized. Okay. Now, so this is what I will call V. Okay. Usually, yeah. Okay. Let's write like this. Okay. And dV I define again just like the definition there as a curl of this. So in other words, I will put here di1 vi2 up to in plus 1 and totally antisymmetrize. Okay, totally antisymmetrize. Just like here, we totally antisymmetrize between xy and y, xy minus yx. But now you do totally antisymmetrize in n plus 1 indices. I mean, there are n indices in the v, and there is one index in the partial derivative, right? There's a direction which we are taking a partial derivative, and you totally antisymmetrize. Okay, and this is what is called dxi1, dxi2, dxi. Okay. Now the statement is the following. For in such case, the statement is that if I integrate dv in a region which is n plus 1 dimensional region, right? We get n plus 1 because see there are n plus 1 dx's. Sorry, n plus 1. Because they are up to n plus 1. There are n plus 1 dx's, so you can integrate it over an n plus 1 dimensional space. Okay. So I take this n plus. That's why I said the dimensional space is greater than or equal to n plus 1. Okay. Otherwise, you cannot do this. So you take an n plus 1 dimensional region. So this is some region in your region which is a dimension n plus 1. And you integrate this quantity. This dV by definition is that, where you have totally antisymmetrized. Usually you put the notation like that, square bracket, which means that you are antisymmetrizing between these indices. Okay. So this what Stokes theorem says that this is equal to the integral of V over the boundary of the region, boundary of R. See, our region itself is n plus 1 dimensional, so its boundary will be n dimensional, right? I mean, take an example. Suppose it was 3 dimension. I mean, this was n plus 1 was equal to 3. Imagine n plus 1 was 3. So you're integrating, for example, on a ball, right? Take a ball, for example, you're integrating inside this. The boundary will be the sphere, right? That will be 2 dimensional. The ball itself is 3 dimensional, but the boundary is 2 dimensional. So this will be n dimensional. Boundary of the region will be n dimensional. And this again I can integrate because V has, you see, n differentials here, n dx's. So you can integrate that. And the Stokes theorem is saying that basically. Okay. So perhaps I should be a little bit more careful because there are some numbers floating around here, which I will be very specific about it. What do I mean by this? There are some factorials, etc., can float around because if I want to take a total antisymmetrization. So in order to avoid these factorials, I will precisely define what do I mean by this derivative, this notation. So di1 vi2 in plus 1 is the same as sum of n plus 1 terms, di1 vi2 up to in plus 1 minus, so di2 vi1 up to in plus 1, i1 i3 up to in plus 1, and so on. You can now exchange, you just exchange. So minus di3 vi2 i1 in plus 1, okay, and so on. So what I'm doing, I'm just taking one of these, say ij here, exchanging I1 with ij, but remembering that I should put the I1 in that position where the ij was, and bring the ij here and then put a minus sign in front to make it totally antisymmetric. Okay. So clearly there will be n plus 1 terms altogether. And of course, see this itself I already started with a V which is totally antisymmetric anyway. Okay. So, I mean, you have to be careful with the position. I mean, you cannot put I1 here, that will give you another sign, right. So the idea is to exchange with each of these guys, say take one of these index somewhere here, exchange I1 with that, but make sure that you put the I1 in that position where the Ij was, because otherwise if you change the position, it will change the sign, right. So that's right. So there will be this n plus 1 terms. This is what I mean by that. Okay. I mean, usually in the textbooks, if you go through the differential geometry, etc., there will be various factorial n's in the definition itself. I mean, you will put a 1 over factorial n, etc., etc. But I don't want to confuse with all that. So this is what it is at this stage. So this is the and how you prove it? It's again the same thing. You take each of these terms. I mean, you first prove it in a hypercube, n plus 1 dimensional hypercube in the full space, right? And then each of these things, I mean, each of these terms is a total derivative. So this one is total derivative in I1 direction. So the result will be, you can integrate the I1 direction, dx I1, you can integrate, okay. I mean, this thing dx I1 you can integrate for the first term, right? And then the result will be just the two boundary terms, right? So, but the remaining integrals will be left over. So that will be the integral over the boundary, or those two boundaries, right, with the relative opposite signs. One will upper limit minus lower limit, okay. So all those signs will come out exactly correctly. For this term will be this total derivative in I2. So you can integrate the x I2 direction, right. So that will be the hypersurface, which is that corresponding boundary of this hypercube, right, and so on. So the steps are exactly identical to what I did in the 2 dimension. Okay. I don't know, maybe is that clear, or should I just do instead of going to the n, just do it for 3 dimension? So okay, let me just do that for 3 dimensions. In fact, that's where you will be mostly using it. I mean, not to confuse with these indices. So let's define some. So now I'll just look at n equal to 2, because n plus 1. So n plus 1 will be 3. So imagine a tensor, which I'll call it f, ij, etc. run from 1 to 3. I and j, etc. from 1 to 3. So I'm taking the space dimension to be also 3. Although it's not necessary, but I'll just do also space dimension 3. So Fij is a totally antisymmetric tensor, second rank tensor. Now I'll define the curl. So let's see how many components are there. These two have to be different because it's antisymmetric. So you have F12, F13, and F23, right? These are the 3 independent components, correct? I mean, this is the same as minus F21 because this is antisymmetric. This is the same as minus F31. This is the same as minus F32. And whenever 2 indices are the same, it is 0, right? So this is all that you have. And now let's define something. So the d of f. So d of f will have 3 indices. Actually, totally antisymmetric. So all the 3 must be different. 1, 2, 3, because my space dimension is also 1, 2, 3. So this is basically, it will have only non-trivial quantities that, and I define this as d1 f23. d1 means d by dx1 plus minus d2 f13 minus d3 f21. Okay. Remember what I'm doing. I exchange these two. I put a minus sign because I want to make it antisymmetric. Then in the last term I exchange these two. And notice that when I exchange, I put the 1 in that position, and there a minus sign. Okay. Right. So now what I do is I integrate this object on a cube, inside a cube. Yeah? Take a cube. So how do I draw this? So let's say this is my x1, x2, and x3 is coming out. The third direction is coming out to the, and I take some hypercube or something like this. Okay. And I want to integrate inside this cube. So I take this guy and multiply by dx1, dx2, dx3, okay, and integrate. Integrate inside this cube. So let's look at the first term. What I will get this total derivative in x1 direction. So I can integrate x1. Okay. So the result will be f23. Now, so let's say I don't know. Yeah. This will be from the upper limit. I don't know what shall I call it, x prime. So the limits are limits. What I should give some name to it. So x1 final. I mean meaning upper limit, right? Upper limit. Let's say upper limit. Then you have y and x2, x3. x2, x3 are still to be integrated, right? So dx2, dx3. Integral over that. So this you see, integral of x1 will give you a total derivative. So it will be this value minus that value, right? So you are integrating over these two faces. One with a positive sign, other with a negative sign, because that's the lower limit, right? So this integral over the, let's say now there are 6 surfaces, right? So this is say surface number 1, minus f23 x1 lower limit, okay, x2, x3, again dx2, dx3. This is on the this surface. What shall I call 2? Surface 2. So into 2. Okay. Then you go through the next one. This will be total derivative in the second direction. So I can do the x2 integral. Okay. And when you do the x2 integral, there will be the two limits are this upper surface, upper thing, and the lower one, right? So then you get the two integrals. The upper integral will be coming with a plus sign, okay, with the x2 upper value, and lower will be coming with a minus sign. Okay. Similarly, the third one you do it. Third one again will be, you can now do the dx3 integral. Okay. This time, so x3 is say this direction. X3. So then I will have the two limits will be say this surface and then the back surface. So you get 6 terms, right? And those 6 terms are exactly those 6 faces around the cube. Okay. So that's the way you prove that. And then okay, you have to be a little careful with all these signs and so on, okay, to show that in fact this is nothing else but the integral of fij dxi dxj over the boundary of the cube. So that, I mean, it's clear, right? There are six integrals, and those 6 integrals are on those 6 faces. Right? And notice that this is indeed true. f23 dx2 dx3. So these 2 indices are the same as those 2 indices. Similarly, so if, for example, if you had done this one, the x2 integral you can explicitly perform. Then what is left over is f13 dx1 dx3. So you see these 2 indices are contracted with those 2 indices. Okay. And you can show, I mean, just try to work it out. You will get 6 terms. And the only thing you have to check, I mean, it's clear that there are 6 integrals over this surface, 6 surfaces. Only thing you have to make sure is that all the signs are coming out right. Okay. So that's something you have to do. But I mean, okay. So this way you see you prove Stokes theorem. You can just go on to any higher dimension. It is the same procedure is the same. Okay. This way you prove basically the Stokes theorem. Okay. This has a lot of applications. For example, here actually, if you let us define some f tilde ij as epsilon ijk, and working in three space dimensions. So there's this epsilon tensor, the 3 space dimensions. So I'm working in 3-dimensional space. Fij is electric field, let's say. So this I take the electric field. So you'll study that. I mean, you've already done electromagnetism, but you'll do more there will be a course on electromagnetism. But I'm just giving an example to show how the Stokes theorem is so powerful. So take this electric field, okay, and I just defined this tensor by using epsilon ijk ek. So I've contracted k. So there is a repeated indices will be summed over. So k goes from 1 to 3. So now let us compute this object. Epsilon, let's say L ij f tilde ij, or let's just do this. D I f j k f tilde j k, and totally antisymmetrized. Or another way to say is that we just take epsilon I j k and divide by 2. That's for reasons which because you see j k is the same. When you exchange j and k, you pick up the same term twice basically, right? Because f is antisymmetric. That's why I divided by 2. Okay. Let's consider this. What is this quantity? This quantity, let's substitute that here. So you get 1/2 epsilon ijk, and then here is jk. So this becomes epsilon jk L EL times di, right? Di EL. I just substituted this for jk. This is jk, so I can write it as jk is epsilon jk L EL, where L is a dummy index. Okay. Now use this relation that, you see, I have contracted 2 of the indices, jk, jk, right? Then you remember, when you do that, it just gives you a factor of 2, okay? Factor of, I mean, there is some factor which appears there. Okay. Factor, actually, I think before it was factorial n minus 1, right? But n is 3 for us, so factorial 2. So that is the reason why this 2 cancels then. So you get here delta IL EL, right? Because jk is contracted, so then whatever it will be Kronecker delta with the index I and L, and this is summed over L, so this is same as EI. Di EL, which is the same as so this means di EI, which is what you call divergence of E, right? This is the definition of divergence of E. So this divergence of E can be written in this way, right, for using this f tilde. But the reason why I'm doing it is because now for this I can use the Stokes theorem. Because remember, for Stokes theorem I needed a totally antisymmetrizing these 3 indices. This was already antisymmetric by construction because epsilon ij is antisymmetric, and then I want to use a totally antisymmetric form construction of these derivatives. This epsilon ijk ensures that this is totally antisymmetric. Okay. So now you integrate this. So now you integrate this quantity. I mean, you see this so you just integrate this expression on a ball. Right? It's a 3-dimensional ball. Okay. Then by using Stokes theorem, this is the same as integral of f tilde jk dxj dxk over the boundary, which is the 2-sphere boundary of the ball, right? So what I'm doing is I'm integrating this expression over so this is some ball, this is a ball, and this is a surface. So let me draw it like this. I mean, this is a ball. Huh? So this integrate I integrate over the ball, and by Stokes theorem this is the same as integral over the boundary, which is boundary is a 2-sphere, right? But now if you put it back, this relation here, this expression, this is epsilon jkl dxj dxk el integral over that, right? Now notice, suppose imagine this was in the polar coordinate. I look at this is my r radial direction, from the center I draw, and then you have this angular variable over the S2, right? So what you are doing, since you are integrating over S2, you are keeping the radial direction fixed, I mean r radius fixed, and just integrating over polar angle theta and phi. So this integral is over theta and phi. Okay, so these are theta and phi. Then j and k are on theta and phi. then L must be the third direction, which is the radial direction. So what this is giving you is just the electric field along the radial direction, and you're integrating over the surface of the sphere, which is the flux, right? So this is the electric flux. Okay. So what this statement is giving you is a relation between electric flux through the boundary, right? And that is equal to the integral of the divergence of E inside the boundary. Right? Now, if you remember the Gauss law, this is divergence of E is nothing else but the charge density, right? So this is giving you the relation. So the integral of divergence of E is the same as the integral of the charge density, right? So it is telling you the total the integral of charge density will give you total charge, which is enclosed in this ball. And this Stokes theorem is telling you that the flux of the electric field going out of the surface is equal to the total charge inside the ball. Yeah. So this is an example of using of Stokes theorem. It's used in many contexts like that. Okay. Any question on this? I've been not very careful with the numbers and so on, factors and so on, but I just wanted to show to you something which you already know from electromagnetism, right? That the flux of electric field is equal to the total charge trapped inside that surface. So this is just a special application of the Gauss law, of the Stokes theorem. Yeah. Okay. So now let's go back to our Cauchy theorem. Can I erase all this now? Okay. Now let me go back to the Cauchy theorem and show that by Stokes theorem it immediately follows. So you have, let's say, Fz. So I have some contour. I choose some contour, and again, for simplicity, let's choose. Okay, it doesn't matter. Choose some contour, and remember this is simply connected, which means this in the entire interior of this closed contour, the function is analytic. Okay. If, for example, in some part it was not analytic, then this will not be a simply connected region, right? Okay. So we are saying that it's analytic everywhere inside. This function f is analytic. In this entire region. Okay. And here is my contour, closed contour, dz. Well, let's again split into its real and imaginary parts. Okay. So what is dz? So what is first of all, fz is u plus iv. These are all functions of x and y. I will not indicate explicitly. It's understood they are all functions of x and y. And the z itself is simply dx plus I dy. Okay. So let's separate out the real and imaginary parts. So the real part will be, so this I can write as u dx minus v dy, right? That's the real part, plus I times u dy plus v dx. Okay, and I'm integrating all of this thing around the closed contour. Okay, see. Okay, now if we want to prove this to be 0, of course, if it is going to be 0, then both its real part and imaginary part must be separately 0, right? So let's look at one by one. So let's look at this term. First, let's do the real part. Okay, so what's the real part? It's u dx minus v dy, right? So now remember this notation. So let me define some vector field whose component x component is equal to u, and the y component is equal to minus v. Okay, then this is exactly what appears in the Stokes theorem on the one side of the Stokes theorem, right? But then the Stokes theorem says that this integral, contour integral, is the same as the integral of the curl of this on the region, in the region, right? Integral of the curl of this, which means dx vy. I mean, I shouldn't use the same symbol. Maybe let me call it A. A is some vector field, because this v can confuse with that v. Okay, so ay minus dy ax in the region, inside this region. I mean, in this entire part here, right? So let us see what it is. This is dx of ay. Ay is minus v, right? So this is minus dx of v, right? And ax is u, so that is minus dy of u, right? But using the Cauchy-Riemann condition, you see that this is 0. I remind you, what are the Cauchy-Riemann condition? The Cauchy-Riemann condition is du by dx. There are two equations, that's equal to dv by dy, and du by dy is equal to minus dv by dx, right? So if you substitute, du by dy is equal to minus dv by dx, so minus minus makes it plus, and that cancels. So this is 0. Since we know that we are saying that the function is analytic everywhere inside, so obviously this function satisfies the Cauchy-Riemann conditions inside. So therefore this is 0. Okay, that was the real part. Now let's look at the imaginary part. So imaginary part, we want to look at this equation, this contour integral of, this integral u dy plus v dx. Okay. Now again, comparing with that, we can define a vector field B such that bx is equal to v and by equal to u. Right? I mean, the x component is the one which comes with the dx, and the y component is the one which comes with the dy. Okay. Now use Stokes theorem, then this is the same as integral over the region of the curl of this vector field, which is dx by, dx of by, but by is u, minus dy of bx, which is v, dx dy, and this is 0. Sorry, this is probably not very clear. Minus is here. So dx u minus dy v, but that is 0 by this Cauchy-Riemann condition. Okay. So this is also 0. So this is the proof of Cauchy theorem. It's just a consequence of Stokes theorem and the Cauchy-Riemann conditions. I mean, this is an important theorem, so please think about it, and if you have any question. At this stage, direction of contour is not important. I mean, any direction is okay. Of course, the Stokes theorem says, Stokes theorem is saying is that this integral is equal to, this integral is equal to that integral with this orientation, counterclockwise orientation. Because remember, when we did this hypercube, I mean the rectangles, the integrals was coming out like that. So it's a counterclockwise direction. Yeah. But anyway, it is 0. So I mean, if the counterclockwise integral is 0, then also clockwise also is 0. But yeah, in Stokes theorem, what appears is the counterclockwise. Yeah. Okay. You see, it's a very two-line proof once you know Stokes theorem, right? Sorry. We should this one or that one? This one. I just wrote the curl. What it will appear here? This is dx of by minus dy of bx, right? I mean, what Stokes? So I just defined. I just called bx equal to v and by equal to u, so that this is in the form that where you can apply Stokes theorem, right? Once you write it like this, this is simply bx dx plus by dy contour integral, right? then Stokes theorem says that this is the same as the integral over the region whose boundary is the C curve, but integral of what? Integral of the curl of this vector, which is dx by minus dy bx, right? But dx by, since by is u, is dx u, and dy bx is v, so that's that, with a minus sign here, and then use the Cauchy-Riemann condition. Okay. So this is it's a lot of applications. I mean, so for example, one consequence of, I mean, here I said simply connected, but you see that if I consider some, I mean, in particular what this says is the following. Suppose I consider two curves like that, two contours, say C1 and C2. These integrals, I mean, let's say, so what this says is the integral over C2 is equal to integral over C1. Okay, if assuming that in this region between the two contours, the function is analytic. Okay, I don't know whether function is analytic here or not. I don't know. Suppose I don't know. Okay, in that case, I don't know if this integral over C1 is 0, because this using Cauchy theorem can be applied only if I know that it is analytic everywhere inside. So, but suppose I don't know. Suppose I don't know whether the function is analytic or not. So I cannot say that C1 integral over C1 is 0, but okay, it will be something, right? It will be something. Similarly, integral over C2 will be again something, but what we are saying is that these two integrals are the same provided the function is analytic in this region, which is between the two contours. Each of them may be non-zero, right? That depends on whether here it is analytic or not. But whatever it is, it will be still equal. And the way to show it is the following: draw a line, I mean any curve which connects these two contours. Okay. Now consider such a big contour. Let's see, you go like that, then instead of continuing, you go like this. No, maybe I should do it. So let's change the orientation. Okay, first let's change the orientation of this. Let's go here. So this is this. Okay. So let me consider C2 minus C1. I want to show that this is 0. I want to show that the integral of C2 fz dz minus integral over C1 fz dz. We want to show that this is equal to 0. Okay, this is a question mark. We want to show that. So, well, minus C1 is the same as changing the orientation of C1, right? Instead of integrating like that, you integrate like that. So minus C1, so the minus C1 integral is the same as going like this. Okay, but I keep C2 the same way. I'm not changing there's no sign. Sign is positive here. Okay, so now draw a line like this, and you say, suppose you start from here. Okay, you come like this, and instead of continuing, you first go down here. Okay, then you continue like that, come back, and then go back along that direction, along the same line, and then continue and come back here, right? I can, so this total integral, I can think of it as an integral over this big contour. I start like that, come here, go here, and come back here. Okay. So, of course, you see, I'm not doing this part cancels. This part of the integral cancels with that part of the integral. So I'm not changing anything, right? So this full integral can be written as an integral over this big contour that I constructed this way. I call it gamma, this big contour. So I integrate over this. But inside this big contour, what is the region? It is this region, right? Where we say the function is analytic by assumption. Therefore, by Cauchy theorem, we know that's 0. So this integral is 0 by Cauchy theorem, because the region, I mean, you look at this contour here goes like that, comes back here. What is the region? It's is a boundary of. There is this region. and there by assumption function is analytic. Therefore, by Cauchy theorem that integral is 0, but this integral is the same as that integral. Right? So you see that this is equal to 0. So another way to think about it is that you can deform this closed contour anywhere you wish, provided the region from where you are deforming. In the process of deformation, you should never cross. I mean, you should always be within the function should be analytic in all that region where you are deforming. When you do that, the result of the integral will not change. This is what it is saying. I mean, so you see, you can deform this contour to that contour, right? But always staying within a region where function is analytic, right? And the integral doesn't change. The result of the integral doesn't change. Okay. That's a very important point here. This, yeah. Now I have how much? Another half an hour, right? So, okay. Another very, very important consequence of Cauchy theorem, and that I will now explain. Okay. It's the following thing, that if f is analytic, say in some region, say around some region near say some point z. Okay, z is some point in your space. Z is some point. When I say z, by the way, this notation just means, after all, z is equal to x plus iy, right? So the real part of z is this coordinate, and the imaginary part of z is that coordinate. So z uniquely specifies which point you are talking about, right? Once you specify z, because z is equal to x plus iy. So just take the real part of z, that is the coordinate here, and the imaginary part of z is the coordinate here. This is the x and y. So that's why, I mean, instead of writing x, y, it is sufficient to write z, because it has all the information about the point. Okay, so some point z, so suppose there is some region where this function is analytic. So suppose I know that it is analytic in this region. Then I can write, then I can consider any path, any closed contour around this, which is entirely contained in the region of domain of analyticity, okay, and which encircles z. Okay. Then the statement actually, yeah. In fact, I will take the two cases. A case where the contour encircles z, and another case where contour does not encircle z. Okay, so let's say a situation like this. Two cases. Okay, so the statement is that 1 over 2 pi I integral of fz dz along the contour C. This is equal to f. Let me call it z prime. Z prime is z prime is a dummy index, right? I'm integrating over. Okay. I mean, if you wish, I can call it. Okay. Z is because I chose z to be this point. I don't want to use the same z here, because this z prime is a coordinate along the whatever contour you are choosing. So this is equal to f of z if contour encircles. So this is a closed contour, encircles z, and is equal to 0, sorry, this divided by z prime minus z, z prime minus z, and it's equal to 0 if C does not encircle. Z. Okay. The second case is immediate to prove. Why? Because if, let's see, I mean, the f is anyway analytic in this entire region, right? Okay. Now, what is the problem with z prime minus z? 1 over z prime minus z. 1 over z prime minus z is analytic everywhere except when z prime is equal to z, right? There it blows up, but everywhere else it is analytic. Now, if the contour, say this contour, if I take this contour, z prime is are points here, right? And inside this region, inside this region encircled by this contour, z prime minus z is never going to be 0, right? So that function 1 over z prime minus z will be analytic in this region, right. So and the product of two analytic functions is again analytic, right. So this will be analytic function, this whole thing is an analytic function if the contour does not encircle z, and then by Cauchy theorem it's 0, right. I mean this is just another, so this is analytic. Let me call this, let's call this contour as C1 and that contour as C2 and this region as R1 and I mean all this region as R2. Okay. So is analytic when z prime is on C1 or in R1. So it is analytic on the contour as well as the interior of the contour. This function is analytic. F already by assumption is analytic. So f is analytic on C1 as well as inside in the R1. So product of this f to that, which is this thing, is analytic in that region, right, on C1 and R1. So by Cauchy theorem that is 0. So the second part is easy. Now let us look at the first part, and to do the first part let me just draw the picture a bit bigger so that you can see more clearly. So for this situation where the C encircles, so here is my point Z, and let's say here is some C. Okay, this is my C. Okay. Now, and so look at this f of Z prime. After all, that is what the quantity is. The integrand is f of Z prime divided by Z prime minus Z. I mean, the only place where this, I mean, this is analytic everywhere here, except at that point, right? Because that's the only place where this blows up, right? So let's do the following. Let's take a tiny circle, a tiny, I mean, I draw it bigger, but imagine this radius of the circle is very, very small, of some epsilon radius of the circle. So I draw a circle around, and okay. Then, of course, already from the previous discussion, integral over this contour is the same as integral over this small circle, right? Because you can deform this contour to the small circle, but always staying in the domain of analyticity, because in all this region it's analytic. So it is sufficient to then just, so this integral over the contour is the same as the integral over, let me call it gamma. Gamma is a circle of radius epsilon. Okay, so these two integrals are the same. So I might as well just evaluate this integral on the gamma, right? Because I am guaranteed the two answers are the same. Okay. So let's evaluate this integral on the gamma. Okay. So I want to evaluate this integral on this gamma, where gamma is the circle of radius epsilon. Now, so this is a circle of radius epsilon. So maybe this is not visible. The radius is epsilon. And eventually I will take the limit epsilon goes to 0, because this is okay for any epsilon, no matter how small, but non-zero epsilon, right? Now, so let's so this is a circle centered around Z, right? So Z prime minus Z must be equal to epsilon times e to the I theta, right? If you use a polar coordinate starting from Z, right? So Z prime minus Z, you remember the Z, when we use the from the origin, if you look at introduce a polar coordinate from the origin, then Z was equal to modulus of Z times e to the I theta. But now I want to, because this circle is centered around Z, so choose that as the origin of your polar system, polar coordinate system. Then Z prime minus Z will be simply epsilon times e to the I theta, right? And theta is going from 0 to 2 pi. As you go around the circle, so this is the angle theta. So this is some point Z prime. So you see Z prime minus Z has modulus epsilon, right? And then there is angle that gives you the phase e to the I theta. So Z prime minus Z is that, which means dz prime is equal to I epsilon e to the I theta d theta. Right? I mean, after all, when I go along this contour, I'm not changing epsilon. The only thing I'm changing is theta. So basically this integral is over theta from 0 to 2 pi. So therefore this integral I can write as 1 over 2 pi I integral f z prime over z prime minus z, which is epsilon e to the I theta, and this measure dz prime just gives you I epsilon e to the I theta d theta. Okay. So this cancels that, e to the I theta cancels that, and I cancels this I. So the result is 1 over 2 pi integral f of z prime d theta. Okay. Now let's write it in the following way. Let's add and subtract fz. Okay. So let me put it like this. So I minus f of z plus f of z d theta. I just added and subtracted this, nothing has changed. Okay, first let's evaluate that term. Here is fz. This doesn't depend, z is some fixed point, right? I'm just integrating over theta. So fz does not depend on theta, I just take it out of the integral, and then the integral of theta is going from 0 to 2 pi, so that gives you 2 pi, which cancels with that 2 pi. So the integral of that simply gives you f of z. Okay. Now there's still the remaining piece, which is 1 over 2 pi f z prime minus z minus f of z times d theta integral from 0 to 2 pi, right? But f of z prime, remember z prime is very close to f z. So I mean f of z prime minus f of z should, I mean, for sufficiently small epsilon, I can make it as small as I wish, right? Will be smaller than some, actually, yeah, maybe I should have called that as delta, and this epsilon doesn't matter. I mean, as you take epsilon smaller and smaller, the z prime is approaching z more and more closely, right? Then this, or another way to say is that after all, we know that f is analytic, right? So which means it's differentiable. F z prime minus f of z divided by z prime minus z, and the limit z prime goes to z, right, is a well defined quantity, right, is what we call df by dz in the limit z prime goes to z. I mean, think of z prime as z plus delta z, then z prime minus z is delta z, right? So this is in the limit z prime goes to z, which means delta z goes to 0 is the same as df by dz, right? It's an analytic function, so we are saying this limit exists. So okay. So therefore we also see that f of z prime minus f of z will be will be very close to, I mean, so let's consider this equal to or minus, yeah, equal to z prime minus z times df by dz plus some small correction, right? Some small correction, maybe let me call it delta, okay? So which vanishes in the limit z prime goes to z, right? That's what this say. I mean, the fact that this, I mean, in the limit this becomes that, right? So whatever the correction is, I mean, now before taking the limit, I'm just writing. So this equal to that plus some delta, actually delta times z prime minus z, okay, in such a way that in the limit z prime minus z prime goes to z, if you want to get that, then delta must vanish. I mean, so let me write. So this is the limit, and the limit is that, right? So before taking the limit, so it will be some delta, right? But what is the statement that since in the limit this quantity is equal to that, so in the limit delta must go to 0, right? And now I just multiplied this equation by z prime minus z, so that's that. So this is equal to this plus delta z prime minus z, where delta goes to 0 as z prime goes to z. That's fine. So using this, we can now try to compute that. What shall I do? Maybe I can erase this part. So let's try to do this. here. So you see, I want to show that this goes to 0. So let's substitute fz prime minus fz is equal to that. So this is the same as 1 over 2 pi. So I'm looking at this term. Let's say term number 1. So term number 1 is this, and substituting that you get here df by dz. You see, df by dz does not depend on theta. Does not depend on z prime, right? It's just at the fixed point z. So I can take that out, and then what is left over is z prime minus z, but that is epsilon e to the I theta. Then you have d theta, right? That's the first term. But that's 0 because the integral is from 0 to 2 pi. This is 0 because epsilon also I can take out. This is the same as e to the I theta divided by I, evaluated between 2 pi and 0. Right? E to the 2 pi I is 1. E to the 0 is also 1. So this cancels. So that integral is 0. And then the second integral is plus 1 over 2 pi, then delta times z prime minus z integral 0 to 2 pi, which is again is 0. Okay. I mean, delta, okay, let me put here. Delta could be in principle a function of z prime, right? Okay. So I should keep it inside. So delta z prime, integral of that over theta. But this again vanishes. I mean, because delta goes to 0 in the limit, z prime goes to 0. So in the limit when the radius epsilon goes to 0, z prime is coming closer and closer to z, right? So in that limit, this delta vanishes. Okay. Actually, this is also vanishing. In fact, it's vanishing doubly, right? So this also vanishes. So what we are seeing is that this quantity vanishes, okay, and so the whole integral is simply equal to fz, which is what we wanted to prove, right? So this is the statement. This is what is called the Cauchy integral representation of an analytic function. So let me just write that down somewhere here. So the formula is very important, so I'll just write the formula again. So this is the Cauchy integral representation. For an analytic function. So f of z is equal to a contour integral over C, and the C is encircles z of f of z prime over z prime minus z dz prime, and then there is a 1 over 2 pi I. Okay. So this is the integral representation. You have some question? Yeah. Yeah. df by dz. df by dz, yeah. Not prime, because, I mean, this is the definition of, this was the definition, right? In the limit, I'm saying that this was the definition. Limit z prime goes to z. This was df by dz at z. Huh? At z. Huh? Sorry? Sorry?
This is appliquer une fonction for to égal sigma z prime moins z for before to.
Oh no, this last integral. You see, I mean. Okay, this even this you can prove. You can do the. I mean, okay, this is a function of z prime. When I write an equation like this, right? This is so what we are saying. This is equal to that plus some small correction, right? Where times z prime minus z. Where this correction. I mean, this delta. By the way, sorry. Those of you who know Dirac delta function. Don't confuse this with Dirac delta function. This maybe delta was a wrong. Okay, it's something. I don't know what shall I call. Not delta. Delta may confuse you with the Dirac delta function. For those of you who know this, okay. But I don't mean Dirac delta function. It's just some function of z prime. Okay. So which has a property that in the limit z prime goes to z, this function goes to 0. That's what we know from the fact that f is analytic. So I'm just doing the integral. First I did so I substituted fz prime minus fz. So first I did that integral, that was 0, right? Then I look at this integral. This integral is also 0 because in the limit the integrand is vanishing very fast, right? I mean this is vanishing because in the limit, I mean this guy is epsilon times e to the I theta, right? As epsilon becomes smaller and smaller, this vanishes, right? The integrand vanishes, and delta z prime is also vanishing. Because if epsilon goes to 0, z prime minus z is becoming smaller and smaller, because after all z prime is the point on the circle of radius epsilon, right, centered around z. So z prime minus z's modulus is epsilon, right? So as epsilon becomes smaller, z prime becomes closer and closer to z, so delta is also vanishing. So this is vanishing even faster than the previous term, right? So that's the point. Fine. Now, this is very powerful. This statement, this representation, and I will remember I made a statement that if a function is analytic, of course, its derivative d by dz exists, right? That is the definition of analytic, but it is not at all clear that df by dz is also analytic, right? But I said that that's also analytic. You see, in the real function, it is not the case. I mean, a function can be differentiable, but its differential may not be again differentiable. But here what the statement is that analytic function is differentiable to any order, okay, and you can prove that by starting from this representation. Okay. So the way you prove it is so let's say we want to, if I try to see what is the step there. Yeah. So first, what I will do is I will try to I will write down an expression for df by dz. Again, an integral representation for df by dz. First, I'll do that. So this was the integral representation for f. Now I will write down an integral representation for df by dz. Okay. So what is df by dz? This was by definition limit delta z goes to 0 of f of z plus delta z minus f of z divided by delta z, right? This was the limit. Okay. So now let us use the integral representation for this, okay. And you find, so this is nothing else. So this is the same as limit delta z goes to 0 of 1 over delta z times that integral of f z prime over z contour c. So I'm taking the, so I have a z here, z plus delta z is here, because remember delta z is, okay, and I take a contour which encircles both the point z and delta z. Eventually I'm going to take delta z to 0, okay. So I just choose some contour which contains both, some contour c. So delta z, z prime minus z minus delta z minus f z prime over z prime minus z dz prime. Yes. So you see, I just use the same expression, just z is replaced by z plus delta z. So this z is replaced by z plus delta z for this one, and that one is as it is. So that's what it is. Now fz prime is a common factor, so this is the same as fz prime, and let's take common factor here. So you get here z prime minus z times z prime minus z minus delta z, and see then you get here simply delta z. Is that clear? Or am I? 1 over 2 pi I, right, correct. 1 over 2 pi I. Okay. I just took, okay, let's take out fz prime outside, because that was a common factor, right? Now take the LCM, right? I mean, this was 1, 1. If we take the LCM, then you'll get here z prime minus z, and here you will get z prime minus z minus delta z, and now the minus and there's a product, right? I mean, this is just the LCM, taking LCM.
You are taking the LCM of what and what?
Initially it was that, right? This was that. I mean, what is 1 over a plus 1 over b, or minus 1 over b? This is the same as ab, b minus a, right?
Yeah. But this part, z prime minus z minus delta z, where is it coming from? The first term.
Ah, where that came from?
Yeah.
That I just used as definition. Here the argument is z plus delta z. So f of z plus delta z is just shift. I mean, instead of z, you write z plus delta z. No, that's what it is, right? So that okay, this is okay. If you want like this, it's like that. Z has been replaced by z plus delta z in that expression. And now you use the LCM. So this call this a and that is b. Then you just get 1 over ab times b minus a. So this minus that. So when you take this minus that, z prime cancels, z cancels, and you just get delta z. So that's what I wrote here. And then you have this integral. That. Okay. So what I'm going to claim is that this expression df by dz is what I would like to so this is what I want to prove. This is equal to f z prime, okay, 1 over 2 pi I integral z prime minus z square dz prime over the same contour. So I would like to prove that this is a question mark. I want to prove that this is equal to that. So let's see. So we have an expression for this here, right? I still have to take limit delta z goes to 0. What am I, sorry, what is it? There is a 1 over delta z outside which I had forgotten, and then I have to take the limit delta z goes to 0. Okay. Now delta z cancels, right? And then in fact delta z goes to 0, you can, this goes out, okay, and you just get z prime minus z square. Okay. So which is that? So that's a way to prove it. In fact, if you look at it, just this expression is just obtained. Remember, f itself was f of z itself was contour integral 1 over 2 pi I dz prime f z prime over z prime minus z, right? So if you just take just df by dz, well, z prime of course is independent and doesn't depend on that. Z only appears here. So if we just taken the derivative of that, so I mean if you just have taken d by dz of 1 over z prime minus z, that is nothing else but 1 over z prime minus z square, right? So basically that's what has happened here. Okay. But the reason why I didn't want to go through that is you see the d by dz was always a bit I mean it was not clear whether you can just do that, right? Because this is like saying that I keep z bar fixed and move the only change the z. Yeah. But I mean it works. It effectively for all the functions which are only functions of z, d by dz is same as taking just naive derivatives. Answer is the same always. Okay. But this way of proving it, I'm not using that. I'm just using the basic definition of the derivative and then showing that that's equal to that. Now you can keep repeating. I mean, now, so this was a df by dz. Now let's ask the question whether this object is differentiable or not, right? So, sorry, can I erase this now? Okay. So, okay, let's take this guy and ask the question. So, let me give a name to that, h, h of z. Okay. This is some, just I'm giving a name to it. So, I want to ask whether h is differentiable, which means h of z plus delta z minus h of z divided by delta z is a limit exist. Does a limit exist? Okay. Question is either a limit. If the limit exists, then you say h is also differentiable, right? So let's check that. After all, h is that. I mean, this is not a question mark. We have proven that. It's that. So let's so this is the same as limit delta z going to 0, 1 over 2 pi I. Okay, there is a 1 over delta z. And then h of z plus delta z is the same as, so once again, you see f of z prime comes out as a common factor. And you get here 1 over z prime minus z minus delta z square. And then minus 1 over z prime minus z square dz prime. Right? I just use this definition. Look at this. Right? And now take LCM again. So when you take the LCM, there will be several pieces. Well, actually, so when you take the LCM, so this is z prime minus z minus delta z square times z prime minus z square, which is then here you get z prime minus z square minus z prime minus z minus delta z square. Right? Now you can simplify this. I mean, remember this a square minus any form. If you have a square minus b square, that's the same as a minus b times a plus b. Correct? This you remember. So since this is of the form a square minus b square, so I can write the numerator. I can write as the difference between these two, right, times the sum of these two. When I take the difference between these two, z prime minus z cancels, and you just get with delta z. So difference. So that a minus b is nothing else but delta z, and a plus b is twice z prime minus z minus delta z divided by the same thing here. Square z prime minus z square. Okay. So that is what that expression inside the parenthesis is. The important point here is that there is a delta z which cancels that delta z. So now, and now of the remaining pieces, you can just take delta z goes to 0 limit. There is no problem with that. And when you take delta z, so this has gone, this cancels with that, right? And when you take the delta z goes to 0 limit, this denominator becomes z prime minus z to the 4, but this goes out, numerator is twice z prime minus z, so one power gets removed, and you find that this quantity is the same as integral 1 over 2 pi I f of z prime, a factor of 2, and z prime minus z cube dz prime, right? So two things we have proven, not only that this exists, but in fact we even calculated what it is, right? So in particular, this exists means this is dh by dz, right? This is dh by dz. So we are saying dh by dz is that quantity. So dh by dz is again an integral representation. But h was itself f df by dz, so this is the same as d2 f by dz2. And once again, you see the same, our naive thing works. I mean, you just wanted to take one more derivative with respect to z. So suppose you just taken naively the derivative inside, and then you take the derivative of this 1 over z prime minus z square, you will exactly get 2. That factor of 2 is coming because of this power 2. 2 divided by z prime minus z cube. That's what it is. Okay. And in fact, now you can, I mean, I will not, you can just keep going, keep repeating over and over again, and then you can show that dn f over dzn at z is equal to 1 over 2 pi I times factorial n. Factorial n, because you see as the powers, so next time when you take a derivative you will get a factor of 3. So it will be 2 times 3. So it will keep factorial n will appear, and then integral f of z prime minus z to the power of n plus 1 dz prime. So this is the basic formula for, so it's giving you a formula for all the derivatives, right? And in particular it is showing that all the derivatives exist. So it's infinitely differentiable. An analytic function is infinitely differentiable, as many times as you wish differentiable. In the book, you will see that these statements are proven in a more general setting, where it was assumed that if a function has an analytic representation, integral representation, not just, I mean, this was a particular integral representation, where what appears here is f itself, you see. But it is proven that even if it was, if you knew that some function can be expressed as some other function divided by z prime minus z contour integral, then again that function is analytic and it's differentiable any number of times, etc. But I will not need it. I mean, it is slightly more general than what I have done here, but this is enough for us. Now, yeah, 2 minutes. Any question on this? This will use, I mean, when we do the Taylor expansions for the analytic functions, actually this will show that the Taylor expansion always exists, because, I mean, we'll use this formulae. So they are quite important formulae. Okay. That there will be at least some neighborhood where the Taylor expansion is convergent. But let me just prove one thing. I mean, in fact, maybe a couple of things I can prove, and then I stop. One thing, a consequence of this, this integral representation is that there are several consequences, but one consequence is that I think it goes under the name of, let me see. No, it doesn't go under any name. Okay. Anyway, it says that if you take a modulus of analytic function, take the modulus of analytic function, modulus of an analytic function, so which means this f of this f modulus, absolute value, then this modulus of an analytic function does not have a local maximum. I mean, what does it mean to say local maximum? It means the following. So if you, so I have the how to plot it now. So here is my x-axis, and say y-axis is here and coming out, and I want to plot the modulus of f. So I mean, let's say here, I mean, I don't know, this is the y-axis. I want to plot modulus of f. If it has a local, so at some point, suppose it has a local maximum, right? Then it means that if you go a little bit away in any direction, the function must decrease, right? Right? It should decrease, because if you are saying there's a local maximum, then locally, of course, later on it can again go up. That's not, when you say local maximum, it means locally, if you go in any direction, the function cannot increase, can only decrease, right? Eventually. So this is the basic statement about the thing. So what one is saying is that this doesn't happen. This cannot happen for an analytic function. There's no local maximum. The way to prove is the following. Right. So, yeah, this basically use the integral representation. So take so f of so suppose I now again let me go back to our usual complex plane picture. So here is my some z, okay, and so of course I'm assuming that in this all this discussion is of course in the domain of analyticity, where the function is analytic. So in this region it's analytic, I'm assuming. So now if it's analytic around here, let me draw a small circle around it. Okay. So this is a circle of radius epsilon again. Radius epsilon. Okay. And we can write down the integral representation 1 over 2 pi I integral over gamma. Gamma is that circle of f z prime over z prime minus z dz prime. Okay. So now let's take the modulus of this. So modulus of f z is equal to is going to be I mean less than or equal to, okay, modulus of, well, it will be modulus of that. So of course 1 over 2 pi, modulus of I is 1. Now I have to take the modulus of that, but that's the same as taking the modulus inside, but it will be less than or equal to because of triangular inequality. Because after all, integral means taking each bit, take little piece to take that, next piece take this and then add them up, right. So it's adding many complex numbers, and using a triangular inequality it will be less than or equal to taking the absolute values of individual complex numbers. So it's okay, that's that gamma, and then the absolute value of that. So you have f z prime, and then okay, so z prime minus, okay, first of all before doing that let me use the fact that z prime is a circle centered around z. So z prime minus z, therefore, yeah, let me first do that. Z prime minus z is equal to epsilon e to the I theta, right, which is what we did already before, right. So dz prime is I epsilon e to the I theta d theta. Okay. So already before even taking this, let me simplify this expression. So this is actually I cancels, so it's already 1 over 2 pi integral 0 to 2 pi of d theta f z prime, and then here z prime minus z is epsilon e to the I theta, which cancels that. So it's just f z prime integral. Okay. And now I just take the modulus of this, so you get integral d theta 0 to 2 pi and modulus of f z prime. I just take this expression and take the modulus of that and use triangular inequality, get this. Now, so on this circle now, okay, this function is anyway bounded, right. I mean it never blows up, it's analytic here, it doesn't blow up anywhere. It will have some maximum on the contour, right. So this will be surely less than or equal to the max of f z prime, right, when z prime is on the circle gamma. Okay. And then but that comes out, and then you can integrate d theta, that gives you 2 pi, and 2 pi cancels. So we are saying that absolute value of f of z is going to be less than or equal to max of the f z prime, where z prime is a point on the circle of radius epsilon, right. So now, so it cannot happen, you see. So what we are saying is that, so let me draw this picture a little bit bigger. Here is my z. I take a circle. I know from this integral representation and that this f of z, absolute value of f of z, will be less than or equal to some point, we don't know which point, but some point on the circle, whatever the maximum of the maximum point on the circle. Now take another circle, again this is going to be less than or equal to some point here, right. Now no matter how close you go, you can always find a point nearby which whose where the function's absolute value is greater than or equal to the absolute value of f of z. So there is no way f of z can be a local maximum, right. In any neighborhood there will be always some point where the maximum of f is greater than the max of f at that point, right? So there is no local maximum. That's an important point. Or you can actually make this, just use the same statement to prove that also if you take the real part of a function, analytic function, or the imaginary part of the analytic function, they also don't have a local maximum. Okay. So if you take the real part, so for example, so if you take let's say e to the power of f z. Okay, this is also an analytic function. You remember exponential is again an analytic function, right? Well, if you take now the absolute value of that, this is e to the power of fz plus fz bar. I mean complex. So I mean suppose f is u plus iv. So this is u plus iv. Complex conjugate is u minus iv. So you get here u plus iv times e to the u minus iv square root, right? That's what the absolute value is. So iv cancels, so you just get e to the 2u, square root is e to the u. So the absolute value of this is simply exponential of the real part of the function, right? But this is also analytic, and what we have proven is for any analytic function. So also that statement says that this has no local maximum. Therefore e to the u has no local maximum, right? So exponential of u is not doesn't have a local maximum. That also implies that u does not have a local maximum, because exponential is a monotonic function, right? It's monotonically increasing. If you increase u, the exponential monotonically increases. So if exponential doesn't have a local maximum, also u does not have a local maximum. Same way you can prove for the imaginary part. Well, all you just have to take is e to the power of, say, minus I f. Take this function. This is also an analytic function. Okay. Take the absolute value. This time you get e to the minus I u plus iv, and then the complex conjugate of that, e to the I u minus iv square root, and this time u cancels. Okay. Minus I times I is plus 1, so e to the 2v, and that's the e to the v. So also v, the imaginary part has no local maximum, because this again is an analytic function. So these are quite strong statements. And finally, also you can show that if you take 1 over f, if f is analytic, so f is analytic, and further assume that f is not 0 in some region, because if it is f becomes 0 somewhere, then 1 over f will blow up, right? So let's suppose, I mean in some region where f is analytic and f has no 0, f doesn't vanish anywhere. Okay. So if in that region, if you take 1 over f is also analytic, right? So this theorem also says the absolute value of 1 over f has no local maximum, which means f has no local minimum, right? In the region where function doesn't vanish. Of course, when the function vanishes, the local minimum is, I mean, absolute value of f is 0, which is of course the lowest possible value. Absolute value is always non-negative, right? But in the region where the function is not 0, what this statement is saying, f has no local minimum. Absolute value f has no local minimum, right? So a lot of nice things you can show. Finally, just the last comment, and then I will stop. There's also another consequence of this integral representation, and that is the following statement: that if the function is entire, you remember the definition of entire. Entire means it's analytic in the entire complex plane. Okay. If a function is entire and is bounded, okay, which means it doesn't blow up anywhere, right? It's bounded. I mean, there's some maximum value. I mean, it doesn't go more than that. So if a function is entire, which means analytic everywhere and in the complex plane, and is bounded. Okay. Then that function is a constant, is a trivial function. Okay. And let me see, this is, yeah, this is proven in the following way. So, see, we want to prove that if this happens, then it's a constant. If it's a constant, that means df by dz must be 0, right? So let's look at the df by dz. Okay. Well, df by dz, again use the integral representation. It is f z prime dz prime 1 over 2 pi I. But now I have a square here, z prime minus z square. Okay. Okay. Now take this z point here and take a large circle now, large circle. Instead of small, take a large circle. This is okay, I can do that. Why? Because anyway, function is analytic in the entire complex plane. So I can choose any large radius circle, and still the function will be analytic in the interior everywhere, right? So I can do that. So choose the radius r. So gamma, the circle. So gamma is a circle of radius r with center z. Okay. Then as we have done many times, z prime minus z is r times e to the I theta, dz prime is I r e to the I theta. So this integral becomes so that you can substitute that, and that integral becomes, so df by dz is equal to 1 over 2 pi. Here you get dz prime. Dz prime is that. So I cancels from here. Okay. Here is r e to the I theta. This is r e to the I theta whole square. So 1 power of r cancels, but the other power remains down. So 1 over r. And similarly 1 power of e to the I theta also remains, because this is only 1 e to the I theta, whereas that square will have e to the 2 I theta. So you have r e to the I theta, d theta, and f of z prime. Okay. So now let's take the absolute value on both sides and use again the Darboux inequality. This is less than or equal to 1 over 2 pi, and well, if absolute value of, so you'll get here, so there's a 1 over r comes out because r is fixed for the circle. You have integral d theta, and absolute value of this, absolute value of e to the I theta is 1, is a phase. So it's just absolute value of f of z prime, right? But we said f is bounded, right? So f is bounded by some number, let's say some b, let's say b is the bound, that's upper bound of f, let's say, the absolute value of f. Then this is simply b. So this is less than or equal to 1 over 2 pi 1 over r times b. So we are saying f of z prime is bounded by some number b, absolute value. Okay. And then d theta integral gives you 2 pi, so which cancels, that's that. So we are saying df by dz is less than or equal to a finite number b, this is a finite number, right, divided by r. But r is as large as you wish, right, because the entire function, that's where the entire function, the fact there is an entire function is appearing. Because for entire function I can choose as large radius as I wish, and still a function will be analytic in that, right. So you can take r going to infinity limit. You can take r going to infinity limit, okay, as large as you wish. And this statement is saying df by dz is smaller than, I mean, so basically that proves that df by dz is equal to 0. I mean, absolute value of df by dz is equal to 0. Sorry.
The norm of f of z prime is less than b, then the norm of df by dz is less than b over f.
Yeah.
So we don't have the equality sign.
Yeah, okay, so let's make it, yeah. But I mean, even saying, even if you put it equal, still you prove the 0, right? Because in the limit r goes to infinity, this is equal to, I mean, the right hand side goes to 0, So, this is yeah. I mean, so df by dz is 0. So this df by dz absolute value is 0, and therefore df by dz itself is 0, because if an absolute value of a complex number is 0, is also 0. Complex number itself is 0, right? So that proves that f is constant, right? I mean, the df by dz is 0, so f is constant. So this is what it is saying is that if a function is entire and is bounded, then it's a very trivial function, it's an uninteresting function, it's only a constant, right? So for any interesting function, if it is bounded at infinity, as z goes to infinity, if it is bounded, then somewhere inside it must have some singularity. Okay. It must have some poles or something it must have, otherwise it's just a constant. Or of course it could be unbounded. I mean, for example, z itself, I mean, if you take the function f of z equal to z, we know it's analytic, is entire, because it's analytic anywhere in the complex plane. However, it's not bounded, right? As absolute value of z increases just as you go farther and farther away. There's no bound in that case. Yeah, okay, I think maybe I'll just stop here. Now, I think next, the only thing which I wanted to do today, but I think it will take some time to do. So what I would want to prove now is that, I mean, next time I'll do it, the converse of Cauchy theorem. You see, Cauchy theorem says if a function is analytic in any region, then integral over any closed contour vanishes. Okay. Now, the converse of the theorem is that if I know that there is a function, okay, continuous function, whose integral over any closed contour in some region vanishes, then that function is analytic in that region. Okay. So it will be the converse of the theorem. So it's like necessary and sufficient condition type of thing. No, but the one implies other implies first. That is the theorem of Morera. And then after that we'll move on to Taylor series, Laurent series, and what else? Residues and so on. Okay, yeah. So we'll move on to that.